Hello? A very good evening to all distinguished resource person, faculty members, and dear participants. I am Dr. S. Dilipan, an associate professor from the GRT Institute of Engineering and Technology. It is my honor to welcome you all on behalf of our institution. We are all gathered here for the 6-day faculty development program on green hydrogen and advanced storage technologies for a sustainable and carbon future. Before we begin, I would like to thank our management and acknowledge their visionary leadership that makes initiatives like this possible. We are especially grateful thanks to Dr. S. Armugam sir, Dean of the GRT Group of Educational Institution and Principal of GRT Institute of Engineering and Technology, and Dr. N. Lakshmi Narasimhan sir, Vice President, Industry Institute Partnership, GRT Group of Educational Institutions. Providing unwavering commitment to academic excellence is a constant inspiring to us all. I would like to extend my thanks to Dr. N. Edwin Paul sir, Professor and Head of the Department of Mechanical Engineering, for this steadfast support in the organizing this program. Our gratitude also goes to Mr. R. Mohan Raj, Assistant Professor and the Program Coordinator from the Department of Mechanical Engineering, whose meticulous efforts have been instrumental in bringing this FDP to fruition. I would like to express our sincere gratitude to the Atal Academy, AICTE, for their visionary initiative for providing us the platform to conduct this virtual knowledge sharing session. I am confident that this FDP will be immensely enriching and stimulating journey for all us all make the most of this opportunity. Once again, a heartfelt welcome to all. Thank you and have a fruitful learning experience. Now, I request Dr. S. Armugam sir, Dean of the GRT Group of Educational Institutions and Principal of GRT Institute of Engineering and Technology, to kindly inaugurate the Atal Online 6-Day Faculty Development Program on Green Hydrogen and Advanced Storage Technologies for a Sustainable and Carbon-Free Future. Thank you, sir.
Thank you, Dilipan. Thank you so much. Happy evening to all the members. It's my pleasure to present the inaugural session and also the welcome address of the FDP program for 6 days, sponsored by the AIST New Delhi. It's our pleasure to convey our sincere thanks to our management, respected Chairman G. Rajendran Ayya, and our respected Managing Director Sri Ananda Pathunavan sir and Sri Radhakrishnan sir. With a great aspirant, our Vice President Dr. N. Lakshmi Narasimhan sir, and distinguished special speakers, Administrative Officer Sri Sachikumar sir, esteemed college staff members, invited guests, participants from various engineering college staff members, organizing convener member Dr. Dilipan, Associate Professor from Mechanical Department, the organizing chairperson Dr. Edwin Paul, Professor from the Mechanical Department. Happy evening to one and all. GRT Institute of Engineering Technology has become the crown jewel in the field of technical education since its inception. The institution was promoted by GRT Mahalakshmi Educational Charitable Trust, and it is governed by the visionary extraordinary philanthropist Sri G. Rajendran Ayya since 2010, whose contribution to the Indian jewelry industry and tourism and the hotel industry remains outstanding. This institution is located on the Chennai-Tirupati highway near Tirupati. It's having a 78 acres with earmarked as a 24.25 acres for the GRT Institute of Engineering and Technology with a robust contemporary architecture benefiting for the global standards. This institution is approved by New Delhi and affiliated to Anna University, Chennai. It's an autonomous institution. This institution got a NAC A++ grade in cycle 1 itself. The institution aims at molding students into the technology sound, efficient, and creative, responsible global citizens for engaging the next generation of the challenges. GRT is run by a team of eminent educationals whose dedication, commitment, and expertise impart quality education blended with the contemporary yet pragmatic touch. It is an historic occasion for all of us today, where we are going to organize the AICT-sponsored 6 days faculty development program in the title of Green Hydrogen and Advanced Storage Technology for Sustainable and Carbon-Free Future under ATAL. This FDP, which was organized by the Department of Mechanical Engineering and GRT Institute of Technology as a part of its regular curriculum. This AICT training learning ATAL Faculty Development Program is a good initiative by the All India Council of Technical Education to enhance the skills of educators across India, ensuring they are future ready and equipped for the demands of a rapid changing and technology landscape. The importance of the ATAL FDP in AICT, it covers the various activities, including the following: skill enhancement in emerging technologies, modernizing the pedagogy, fostering research and innovations, career advancement and professional growth, institutional credibility and accreditations, aligning with the National Education Policy NEP 2020, national development, etc. It's our privilege to welcome our session-wise chief resource person with their great busy schedule also. The following session caretakers are given their consent to give the wonderful presentation for our 6 days program. Session 1 today we are going to start in the topic of introduction to green hydrogen, production pathway and global trends. The name of the resource person expert is Mr. G. Dhanasekaran. His resignation organization name is Senior Manager Engine Design. Senior Manager Engine Design, same duties, Pasar Private Limited, Ranipete, Tamil Nadu. And the session 2 taken care by topic name is Electrolyzer Technologies, Alkaline, PEM and SOEC Systems. The name of the resource person is Dr. S. Tyagarajan. He is Associate Professor, Alliance University, Bangalore. And session 3, the day 2, topic name is Harnessing Solar and Wind Power for Electrolytic Hydrogen Generation. The name of the expert is Dr. Vedaraj Sir, organization NIT Trichy, Tamil Nadu. The session 4, second day, second section, Smart Grid Power Electronics for Hydrogen-Based Energy System. The expert name is Mrs. R. Shobana, and she is the Senior Engineer, Metro Thermal Power Station, Salem, Tamil Nadu. And session 5, the topic name is Advanced Hydrogen Storage, Solid State, Liquid and Compressed Gas Options. And the research and the expert name is Dr. Gokulraj Saktivel Sir. He is a professor in Chengshu University, Taiwan. In session 6, the topic name is Hydrogen Supply Chain Distribution Infrastructure. Expert name, the resource person name is Dr. V. Karthikeyan. He is Associate Professor, Dr. NGP Institute of Technology, Coimbatore. Session 7, topic name is Hydrogen Mobility, Fuel Cell Electricity and Heavy Transport. The resource person name is Dr. Nandagopal Sir. Organization name is Professor, School of Electrical Engineering, School of Mechanical Engineering, VIT University, Vellore, Tamil Nadu. And session 8, Hydrogen for Industrial Decarburization, Steels, Ammonia and Refining. Name of the expert name is Yashwantir Aryan for Associate Professor, National Cheng Kung University, Taiwan. Session 9, topic name is Generation Energy Storage, Solid State Batteries and Flow Batteries. Expert name Mr. P. Dinagaran Sir. Is a manager, Royal Enfield, Chennai, Tamil Nadu. Session 10, topic name is Hybrid Energy Storage System, Hydrogen Battery Integrations. The name of the expert is Mrs. S. Thirumalai Vallavan. Organization name is Senior Engineer R&D TVS Brake India Limited, Chennai, Tamil Nadu. Session 11, topic name is Policy Frameworks, Incentives and Global Roadmaps for Hydrogen Economy. The resource person name is Dr. Vimal Jayaseelan. Organization name is Founder and CEO of High Mobility Madurai, Tamil Nadu. Session 12, topic name is Techno-Economic and Lifestyle Analysis of Green Hydro Projects. Expert name or resource name is Mr. Manigandan and is working as a CEO of Lakshya India Auto Technologies, Tamil Nadu. Session 13, Case Studies, Innovation in Hydrogen and Storage Tech. The expert name is Mr. Jayachandran. Organization Senior Engine Designer, High Mobility, Madurai. With these great 13 sessions, we are going to organize the 6 days FDP program. Faculty, with the support of Atal, we are going to organize in a meticulous manner. Once again, on behalf of GRT Institute of Technology, we heartily welcomes you all for this special FDP program, the title of Green Hydrogen Advanced Storage Technology for a Sustainable and Carbon-Free Structure. Once again, welcome you all to this program. Before that, it's a small introduction, some of the key parameters. It's our duty to convey the participants. It's an important instruction for the entire 6 days program. Kindly join at least 5 minutes before prayer of this session. And also one of the important note, kindly avoid joining the online FDP, those who are in two-wheeler traveling based for their safety purpose. Kindly avoid to join the FDP, those who are using the two-wheeler traveling for the safety purpose. Enter your full name when you are prompted there, click on joining the FDP program. You will be automatically allowed into the session if you join during the session. Kindly note that your mic will remain muted throughout the session. Kindly raise your hands during query times so that we will be unmuted to ask for the queries. As soon as each session, end of the feedback link will be provided. Kindly fill the same promptly. Issues of certificates. Certificates, important note. Kindly please make a note all the participants. Certificate will be issued only to the participants, those who have attended 80% of the sessions and secured 70% of marks or more in the test. Kindly join, follow all the rules and regulations of the FDP. Kindly join and support, enhance your idea. All the best for we pray for successful of the 6 days FDP program. All the best for the participants. All the best for Dr. Dileepan. All the best for Dr. Edwin Paul. God bless. We'll have a fruitful 6 days. Thank you. Once again, welcome to all. Thank you so much. Thank you. Hand over to Dileepan, sir.
Thank you, sir, for your valuable speech. Thank you, sir. Now, I request Dr. N. Lakshmi Narasimhan, sir, Vice President, Industry Institute Partnership, GRT Group of Educational Institution, to deliver the special address. Sir, please.
Yeah. Am I audible to you all?
Yes, sir. You are clearly audible.
Thank you. A very good evening to one and all present here. And really, my heartfelt congratulations to Dr. Dileepan and Dr. Edwin Paul of Department of Mechanical Engineering of GRT IET for organizing such a great program. It's really a great topic of the day. The day we are speaking about a carbon-free environment, then the decarbonizations and the climatics and lot many associated issues connected to climate change and whatnot. So, and also the energy hungry community of ours. So we are speaking of a lot of energy developments, a lot of energy generations, then the improvisation of the energy capabilities of India, because we are marching towards $1 trillion economy population. So therefore, talking about energy and meeting our energy goals in terms of sustainability, everything, these are all the talks of the day, and it's at the right time that such a green hydrogen kind of topics is being organized as a kind of an FDP for eliminating the faculty members with the right knowledge and intention to drive towards the carbon-free economy zone. Thanks a lot for arranging such a beautiful, well-coined topic for the FDPs. And also, it's very interesting. So when we talk about the green hydrogen, no doubt, the National Green Hydrogen Mission has been set for this accomplishing the 5 million metric tons of green hydrogen production per annum right in 2030. And if you look at the scales, we indeed need to have a kind of 125 plus kind of gigawatts of renewable energy production to meet out this challenge. And if we want to meet out this challenge, what is the ultimate benefit? It's 10x. That is, for every 5 million tons, we have like 50 million metric tons of CO2 can be erased out from this planet. So that is the one kind of contribution that we have. And to the tune of several 8 lakh to 10 lakh crores of investment again is needed, I feel so. So it is not that easy. Why India is being looked at for green hydrogen production is the kind of space that we have for renewable energy generation, the kind of scope that India can materialize itself in terms of production of renewable energy through use of solar or through use of wind and whatnot. So all governments, all ministries should come together in order to realize this effect. So not only one ministry of renewable energy can come and kindly come and meet out these requirements. It is from the manufacturing side, for example, the steel manufacturing of steel, which consumes a lot of hydrogen, and those Ministry of Power and also the distribution and the transport, every ministry should come forward to in order to realize this green mission, green hydrogen mission. So in this context, I welcome such a move from the academia to promote such kind of technologies in terms of knowledge sharing, in terms of inviting industries to share their experience in hydrogen production, hydrogen manufacturing, hydrogen safety, hydrogen handling, and whatnot. So therefore, these 6 days are going to be really enthralling and enthusiastic for all of us to listen to the people, to listen to the experts, and find out spaces for our own projects being done in this area towards a green mission, towards a green hydrogen mission is further really going to be scintillating for us. And thanks a lot for GRT-IET. Thanks a lot to all the participants. Thanks a lot to all the speakers, those who are going to be heading us with the knowledge sharing for the next 6 days to come. So make use of this opportunity. And thanks to the principal of GRT-IET for organizing such a brilliant kind of an FDP. And thanks to all the brains behind this. And one and all, thanks a lot. And make use of this. And please visit GRT-IET campus at Tirutani anytime for any kind of associations, any time for sort of collaboration for R&D and whatnot. Thanks a lot for all of you for giving me this opportunity, and thanks a lot. Bye.
Thank you for your excellent talk, sir. Your insights were clear and very helpful for all us. Thank you, sir. Now, I request Dr. Edwin Paul, sir, Professor and Head of the Department of Mechanical Engineering, to deliver the special address. Sir?
Okay, thank you, Dr. Dc1, sir.
Thank you, sir.
Good evening to everyone joining us today. Our respected Dean, Principal, and respected Vice President, sir, distinguished resource persons, faculty participants from various institutions across the country, and my dear colleagues. It gives me great pleasure to welcome you all to this online faculty development program. Even though we are meeting virtually, the participation from across the country reflect the growing importance of today's theme, green hydrogen and advanced storage technologies. In the current global energy scenario, green hydrogen has become a powerful solution for decarbonization. Produced using renewable energy, it is a clean, carbon-free fuel that can significantly reduce emissions in industries, transportations, and power systems, especially in sectors that are difficult to decarbonize. Its flexibility and wide range of application made it a key component of future energy solutions. At the same time, the rapid growth of renewable sources like solar and wind demands advanced energy storage technologies. Since renewable sources are intermittent, storage systems such as batteries, thermal storage, and hydrogen-based storage are essential to maintain grid stability and provide reliable round-the-clock energy. Together, green hydrogen and modern storage technologies form the foundation of a sustainable energy future. They strengthen energy security, reduce dependence on fossil fuels, and support global efforts towards a carbon-free world. One significant advantage of an online FDP is that it enables us to bring together experts, researchers, and participants from different regions on a common platform. Over the next few days, you will have the opportunity to learn from academicians and industry professionals through virtual lectures, demonstrations, and interactive sessions. Participants will gain insights into green hydrogen production, storage, and applications, advantages in battery and non-battery storage technologies, safety consideration, policy frameworks, and energy industry trends, research opportunities, and future directions in clean energy technology. I encourage all of you to stay engaged, ask questions, and actively participate to make the most of this learning experience. Whether online or offline, the true value of this FDP lies in the knowledge you gain and the collaboration you build. I extend my sincere appreciation to AICTE and Atal Academy for their support. To our respected principal and Vice President, sir, for continuous support and guidance, and to the FDP coordinators and organization team for their dedication in planning this event. I wish everyone a meaningful and enriching online learning experience. Thank you. And once again, welcome to the program. Hand over to Dileepan, sir.
Thank you for sharing your expertise with us, sir. It was very informative and engaging section. Now, I request Mr. R. Mohan Roy, sir, Assistant Professor and the Program Co-Coordinator, Department of Mechanical Engineering, to deliver the introduction of the session, one speaker. Good evening to all esteemed participants and dignitaries. It is my distinct privilege and honor to introduce our expert speaker for the session 1, Mr. G. Dhanasekaran, Senior Manager, R&D, Engine Design, SAM Desk for India Private Limited, Vanipet. Its industry experience offers a vital bridge, cutting-edge research and real-world engineering application in sustainable power system. We are gathered here to gain insight from a professional whose career is a masterful blueprint of dedication, continuous learning, and specialized expertise in the field of mechanical engineering. Mr. Dhanasekaran sir built a strong academic foundation by completing Diploma in Automobile Engineering and MTech in Mechanical Engineering. His professional journey with 1998 to 2004 worked as a Soy Forge Private Limited, gaining his first industry experience. The core of his career is defined by the profound contribution to the automotive and tractor industries. From 2004 to 2007, Sir has worked as in the SAM Desk for India Private Limited, after which he contributed to the TEFE from 2007 to 2008. In 2008, Sir joined as an Alkaline as a product development manager, and in 2003, Sir as in the position of promoted to the deputy manager. Spent 15 years at Alkaline. Overall, his Sir journey from 1998 to 2024 shows a ready growth from shop floor experience to R&D leadership role. Built in more than 25 years on practical and hands-on knowledge. With great pleasure, let us warmly welcome Mr. Dhanasekaran sir. The session is now hand over to the sir. Sir, please welcome, sir.
Thank you. Thank you very much, sir. Good evening, everyone. It's a truly...
Good evening, sir. Good evening. Welcome to the session, sir. Good evening, sir.
Thank you. Thank you, sir. Thank you for detailed introduction on me. It's a truly privilege with you today to discuss on this most promising frontiers in our global energy transition, green hydrogen. As we all know, the world is at a critical j- juncture. The challenges of climate change, raising energy demand, and the urgent need of sustainable and solution have brought us to point where innovation is not just desirable, but essential among the many pathways being explored. Green hydrogen science as a clean, versatile, and scalable energy carrier that can transform industry, power of our cities, and help us achieve net zero goals. Today, I will take you through the fundamentals of a green hydrogen. What is it? How it is produced, and why it matters. We will also explore its application across sectors from transportation, power generation, some industries, production industry also, and look at the global projects that are already shaping its future. Many players are working towards on this. My goal is very simple to make this complex topic accessible, inspiring and relevant to each you where you are student or researchers, policymakers. Yeah. Together, let us imagine future where clean energy is not just an aspiration, but reality powered by green hydrogen. Yeah, I'll share my screen. Let's begin. Can I share my screen?
Yes, sir.
Yeah. I hope my screen is visible now.
Yes, sir. It's showing.
Yeah. Put it in. Just a minute, sir. Yeah. Today we are talking about green hydrogen. The content of this presentation is definition and importance, then production methods, production pathways, and global trends and market outlook. Then challenges, future prospects and roles in energy. Just a minute. Yeah. What is green hydrogen? First of all, produced via water electrolyzers powered by renewable energy, solar, wind, resulting in zero GHG. So emission, contrast with gray fossil fuel and blue fossil based carbon hydrogen, those are not covered in green hydrogen. Key attributes are zero direct CO2 emissions. So high energy density and versatile carrier enables decarbonization of R to abate sectors. Today we know that the hydrogen produced in which process that defines the color of the hydrogen. Now we are going to review the green hydrogen. Okay. If you see here, uh, I shown here green, gray, and biomass gasification also is there. That is also one of the green hydrogen, and catalyzed PEZ also is there. If you, the picture, right side picture clearly explains the which, green hydrogen, the windmill, and solar system. If we use a solar system or wind, renewable energy, then water. Just a minute. Yeah. This is a comparative overview of hydrogen production methods. If you see here, I'm showing here, steam methane reforming. The natural gas reacts with steam to produce H2 and CO2. The separation is happening. So fossil fuel, natural gas is the energy resource. Then efficiency will be the 65 to 70%. The cost range is $1 to $2. The effect of this hydrogen is high CO2 emission will be the most common today, can be paired with CCS, carbon capture storage. If we consider carbon storage, then this will be a blue hydrogen. Okay, yeah. Then again the coal gasification, coal reacts with oxygen and steam. The H2 is produced. Then we are using a coal is the median for this. The efficiency of this gas is 45 to 50%. Then the cost is very low, $1 to $2. Then the carbon footprint is high, used in coal-rich countries, environmentally damaging. The electrolyzers, splitting water into H2 plus O2 using electricity, renewable, solar, wind, hydro. We consider this one as a green hydrogen. The efficiency will be around 60 to 70%. The cost will be higher in the what we predicted, 3 to 6 US dollar per kg. So zero, the carbon footprint will be the zero. Green, what we call it as a green hydrogen. Cost expected drop $1 per kg by 2030. That is the vision and the target of our country. Then there is one here. If you see the already matured process, the first two row is already matured process, and electrolysis, alkaline alkaline PM and solid oxide is growing now. Every OEM and research institutions, everyone, they are working on this. Now we are targeting this electrolyzers H2 gas. Other three mentioned here is under R&D level. The efficiency of this H2 gas production is very, very less, 35 to 50% only. The cost will be around 2 to 5 US dollar per kg. The carbon footprint will be low or moderate. There are other two methods also there, but those are under R&D only. I'm jumping to another, the electrolyzers. How the H2 produced in through electrolyzers method is a very simple. Alkaline water electrolyzer, what we call it as AWG, measure low cost, 60 to 80% efficiency, suited for large scale study operation. The right feature clearly shows that the water we are giving input, then left side is the anode and right side is the cathode. The PM passing through this catalyst and we are splitting water plus hydrogen is the output. Another side water plus oxygen. So we are splitting H2 gas here. In India approach, future green hydrogen hubs across India. Here is a regional breakdown of India's emerging hydrogen ecosystem. Hydrogen Valley Innovation Cluster, HVIC, launched in November 2025 under National Green Hydrogen Mission 2023. The Gujarat is the hub for this. Major projects are by Reliance, Adani, and other energy producers focus on export and industrial usage. Then another now Karnataka, there is one ACME group and state government collaboration for green hydrogen production. There is another program, Kerala, Vijinjam Port and Kochi, Trivandrum corridor for banking. So Odisha also they are working. Rajasthan Inox Air products they are working by NTPC projects hydrogen. Then there is one more project in Tamil Nadu emerging interest in coastal hydrogen infrastructure potential link to export corridors. So our strategic goal is by 2020 is 5 million tons of green hydrogen annually, 500 gigawatt of non-fossil fuel energy capacity. So our target is targeting $1 per kg hydrogen production cost target. So global export leadership in green hydrogen and derivatives. The approach is very clear. India's approach. Indian Green Hydrogen Mission 2023 they formed. Then they launched to make India a global hub for green hydrogen production and export. The target investment is 8 lakh crore and aim to create 6 lakh clean energy jobs. Cost reduction now, as we discussed, current cost is around 4.5 dollar per kg. The coal reduced to $1 per kg by 2020. That's our target. Enables competitiveness with fossil fuel in steel, fertilizer, mobility, and heavy transport. Strategic partnership. Hydrogen diplomacy with the Gulf nation and Europe. That is a strategic partnership we made. And India, Middle East, Europe economic corridor for hydrogen exports. Renewable energy integration is leveraging low-cost solar wind power, local electrolyzer manufacturing to cut cost. Our vision is global leadership by 2020. The position India as the world's lowest cost green hydrogen producer by 2030. Transform industries, reduce carbon footprint, and boost circular economy innovation. The challenges in scaling green hydrogen is high production cost. As I told you, at the moment, $4 to $5 per kg. We are targeting 1 kg per $1 per kg by 2030. The electricity cost is 65 to 70% of a total. When we talk about a supply chain and infrastructure, electrolyzer capex, there is a we are targeting electrolyzer capex and critical materials, pipelines, storage, and refueling stations. That is a very important near future. Then demand and certification need of offtake agreements, policy mandates, and harmonized standards. Now, each and every um, research and government bodies are working towards the standard formation and policy. The whole team is working on this. Then environmental and social, water and land use, community engagement, life cycle assessment. Yeah. Future prospects and role in energy transitor is decarbonization, essential for net zero target in hard to abate sectors. The energy storage, that is another future prospects. Then global trade, innovations, lot of innovations is required from research oriented institutions and government bodies, from OEMs. A lot of OEMs are working uh, on innovating the application and production. Then just transition, job creation, regional development, and energy security. In green hydrogen, there is one method, steam methane reforming, SMR technology. The technical details is process, its emission cost, cost emission 7.5 and 12 kg CO2 per kg of H2 produced. The blue hydrogen integrates carbon capture up to 90% of removal, but upstream methane leakage remains concern. This is the pictorial representation on electrolyzers. Just a minute. Oh, sorry. I lost. Sorry about yeah. My screen is below. Sorry. Mr. Dilipan, screen is visible.
Yes, sir, visible, sir.
Yeah. Sorry, I lost. And just a minute. I'm audible?
Yes, sir. Audible, sir. Screen also showing, sir.
Sorry
Okay.
for this. Yeah. Sorry. Yeah, I am back. Yeah. When we see the parameters and different methods, the temperature in KOH method, the temperature will be around 60 to 100, and the polymer solid formal 50 to 80. The ceramic method of 700 to 850, and alkaline. This is a table clearly shows the difference between the different process methods. And biomass gasification is the another method of producing gas. And here now convert organic matter into the sink gas at 700 to 1200 degrees centigrade can achieve negative emission with carbon capture and storage. There is another method, thermochemical water splitting method, and here no photocatalyst and method, direct solar driven, and water splitting using the semiconductor and catalyst. There is another complicated method is biological hydrogen production method. Lot of R&Ds are going on this method. The dark penetration and photo penetration, biophotosis, and microbial electrolysis cells they are using. The advantages and the challenges of hydrogen. The advantage is utilizes waste material in bio, and low energy input requires potential for integration with biorefineries. The challenges of this one is low hydro, hydrogen yields, difficulty in scaling up production, process optimization, and complexities. Downstream purification also is the challenge, one of the challenge. The comparative assessment of hydrogen production methods is, SMR method, the GHG emission, per kg of CO2 per kg of hydrogen, it emits 9 to 12 kg of CO2. The water usage around 9 liters per, per kg of hydrogen. The typical cost would be around 80 to 120 rupees. If we make through SMR plus CCS, the carbon storage method, the color coding will be the blue. Emission 2 to 7 CO2 per kg of hydrogen. Then water will be around remain 9, and typical cost will be the 160 to 200 rupees. Today's topic about green hydrogen. One of the method is the electrolyzers. The emission is 0. We mentioned now there is a, if we powered by renewable, then it is a 0. If we go with CCS method, then the negative CO2 emission. So again the water usage will be the remain same 9 liters per kg of hydrogen. The cost is around 360 to 480. And biomass is a challenging one. The gas, as I told you, the negative side are some. If we go with carbon storage method, that will be negative. Then water usage will be the high, 10 to 15 liters per kg of hydrogen. Then a typical cost will be very, very less, 2 to 5. But efficiency will be very less. Similar way, the photocatalyst and biological, those are under experiment. So the cost is not available at the moment. The production pathways, electrolyzers with renewables, most nature green hydrogen pathway, integrating with the solar, wind, hydro, rapidly scaling with global electrolyzers capacity projected to reach 230 to 520 gigawatt by 2030. Sorry. If we consider photocatalyst and PEC, direct solar to hydrogen conversion, promising for future cost reduction. Key research focuses on catalyst development and reactor design and scale up. There is another method, biological method, includes dark penetration and photo, but the yield is very, very less on this method. Renewable energy, the electrolysis emerging with the renewable energy, the grid connected hybrid system. There's electrolysis manufacturing and supply chain is the again challenging one. India is focusing on this. The key trend on this, focus on cost reduction through scale and automation shift. Lot of R&Ds are going on this. At the moment, the global trends market, if you see here, so many countries and so many research institutions and OEMs are working on this. So hydrogen demand exceeds 90 million tons per year at the moment in 2025, with the green hydrogen rapidly growing from less than 1% of a supply. Project boom. Over 1,500 green hydrogen projects announced globally, targeting, as I told you earlier, 230 to 520 gigawatt. The, now leading the regions, now China is the leading this developments, and a lot of R&Ds are going on. Then Australia, EU, European Union, then United States, India also we are working towards on the this target. South Arabia, Oman, Chile, lot of countries are working. The market value, when we talk about market value, the green hydrogen market is expected to reach 7 to 9 million dollar by 2030, with India alone contributing significantly. That is our target. The major players globally working in hydrogen, no, the Western Green Energy from Western Australia, they are targeting 50 gigawatt through solar and wind. H2 output they are targeting around 3.5 metric ton per year. This is one of the world largest renewable hub. Then Haman project, Mashed, no, they are targeting 30 gigawatts through solar and wind. If you see here, we are India also working. Pudimandaka Hydrogen Hub, located in Andhra Pradesh, India. We are targeting 7.2 through renewables. 0.6 metric ton per year we are targeting. Then Greenco is the partner for this one. India flagship for hydrogen hub. The similar way, China, no, if you see here, China, they are dominating in lot of electrolyzers manufacturing, and they are the solution providers at the moment. And Australia and China is the leading. They are in front of us. The hydrogen infrastructure and the storage, transport and carriers. The storage, 752. The compressed gas pressure will be around 350 to 700 bar. That is the most challenging one. The liquid hydrogen now minus 253 degrees centigrade, solid state. The transportation pipeline, existing and new, blending with natural gas up to 20% and shipping liquid hydrogen, ammonia. This is every country and government bodies are working towards this. The transportation of this hydrogen and storage is the critical area. If we talk about India specific context and national strategy, as we discussing National Green Hydrogen Mission (NGHM) launched in 2023. We are targeting 5 metric ton per year green hydrogen by 2030. 8 lakh crore rupees they are planning to invest on this program, and incentives for electrolyzers and manufacturing production R&D infrastructure skill development all over India. The government is approaching and guiding us. The green hydrogen standard, less than 2 kg of CO2 per kg of hydrogen. That is our target, 12-month average, 1 year. Major projects. Kudi Madaka, Tamil Nadu, Adani Total Energies, GAIL also working, IOC, NTPC, everyone, they are giving their contribution for these major projects through policy tools. Waiver of transmission charges, says support, then single window clearance, environmental exemptions, export strategy. We are targeting 10% of a global market. India will be the player for this. We make a partnership with European Union and Japan, Australia. Challenges. What challenges are now? Land, water, grid integration, electrolyzer, supply chain, cost competitiveness. Lot of certification scheme is going on, still under they are framing the standards. Lot of standards already in preliminary standards are available, and many OEM players are working on this. The key elements what we consider for the mobility or industrial usage is emission intensive threshold, then renewable electricity sourcing. Additionally, guarantees of origin, digital certification, alignment with international trade and WTO rules. The conclusion of this one is green hydrogen in clean energy transition, electrolysis using renewables is the leading green pathway with rapid scaling and cost reduction. Global market momentum is strong, but challenges is in cost, infrastructure, certification remain. Major projects and policy frameworks are shaping the future landscape. Academic institutions have vital role in research, education, and workforce development. So, yeah, and I'm going to touch upon this the application in automobile engines, hydrogen engine system, combustion engines. Just a minute. Sorry. The introduction, when we talk about hydrogen engines, hydrogen engines reference the pivotal advancement in automobile technology, leveraging modified internal combustion engine to run hydrogen fuel. In India, many OEM players are working with other fuel manufacturers like Reliance, IOCL. Many OEMs are working with these oil companies, and a lot of R&Ds and a lot of things is going on this. This is where, when we talk about hydrogen engine, this is very similar to SI spark ignition engines. The change of component, it will be very similar to CNG engines. Some of the component, we need to make a modify. We will go through this. Why hydrogen as a fuel is a abundant and renewable, zero carbon, no, zero carbon content, high energy. The energy density in hydrogen is exceptional. So the retrofit capability is quite possible on SI engines. When we talk about hydrogen properties and relevant to engines, understanding hydrogen's unique properties is crucial for successful engine design and conversion. The characteristics profoundly influence combustion dynamics, storage requirement, and safety protocols is the major role here. Very low ignition energy. The hydrogen requires significantly less energy to ignite compared to gasoline. Increase the risk of a pre-ignition and a knocking. Engine knocking will happen. Backfire also sometimes make no difficulties. Yeah. Then low density. Hydrogen, when we talk about hydrogen, low volumetric energy density, necessity high pressure storage solution such as compressed gas tanks is required to achieve practical driving ranges. Okay. The flammability range is 4 to 75%. This is a broad range when we compare with no conventional SI engine. The flammability range is too high. Highly diffusivity, so it easily mix with air. That is one more property. The high flame speed. High high flame speed, we need to modify the combustion chamber, and the material of the piston has to be taken to the account. A lot of R&Ds are going on this. The piston rings and the liner properties and material has to be uh, robust enough to withstand this high flame speed. The hydrogen combustion basics, when we talk about this one, that while clean and high combustion temperature can lead to the formation of nitrogen oxide, so it may need, it is required the catalytic converter for this. A three-way catalytic converter is essential to control the NOx. If not properly controlled, this requires carefully engine calibration and potential exhaust after treatment system. So the engine calibration is also the another challenge for this hydrogen engine, H2 ICE engine. We need to take into the account of pre-combustion, backfiring, knocking, the safety, everything has to consider during engine calibration. The key benefit of hydrogen is the ability to support ultra lean combustion. This means the engine can operate with a much higher air fuel ratio than traditional gasoline engine. Why? Because as we discussed, highly diffusivity, the property. So the air fuel ratio will be good. The combustion process in hydrogen engines. In spark ignition engine, hydrogen, the combustion process shares fundamental similarities with the gasoline engines, but incorporates critical difference due to hydrogen unique properties. The hydrogen and air mixture can introduce either via port fuel injection into the intake manifold or direct into the combustion chamber through high pressure direct injection. So at the moment, many OEMs working, the port injection method only, PFI. The spark ignition, it's similar to gas engines. A spark plug initiates the combustion. However, hydrogen very low ignition energy necessitates precise control to prevent unindented ignition. The rapid flame development also is a combustion process. This leads to the early flame development in hydrogen combustion is significantly faster than that the gas line. The ignition timing is the another challenge. We need to we need to work closely on during the engine calibration. The challenges of combustion, as we discussed earlier, the pre-ignition will be the one of the major challenge. Hydrogen low ignition energy makes the engine susceptible pre-ignition for hot spot. Example, spark plug exhaust valve leading to uncontrolled combustion and potential engine damage. There is another, we need to consider backfiring, where combustion occurs prematurely in the intake manifold is a significant risk in port injection hydrogen. Okay. There is another challenge is knocking tendency. So high NOx emission. So it may need very good engine after treatment system is required. The volumetric efficiency of the reduction is the another challenge. What modification is required for hydrogen engine? If you see here, hydrogen compatible injector is required. So since the temperature will be so high, we need compatible injectors. Then injection strategy, port injection or direct injection, that has to be optimized through various taste and visual analysis. Then we need a backfire arresters. So here now, strong engine modification in ignition system is strong ignition coil is required. Then optimized spark timing, modified plug design. Then ECU remapping is required. See, here ignition coil now hydrogen l- lean burn capability. So it's may misfires under the certain conditions. So we need to focus on ignition coils and spark plugs. Okay, the timing also now. When we consider the backfire and pre-fire, we need to optimize the timing through various exercise and various analysis, visual analysis. A lot of experiment has to do to optimize this timing. Then modified plug design is required. ECU, the uh, calibration is required for this. The new piston crown design is required when we consider flame speed is so high and the temperature. When we consider all the things, new piston crown design is required for this one. Then material upgrade to withstand high temperature, and this fuel properties. So many oil has to um, optimize for these changes. So the components like valves, wall seat, and cylinder heads may require material with enhanced heat resistance and durability to withstand these conditions. So compression ratio also to be optimized based on the efficiency of the engine to engine. We need to optimize the compression ratio. The cooling system uh, also is the risk free ignition and ensure the engine in exhaust system. What has to be considered now? NOx catalytic control. So three-way catalytic control robust uh, enough design is required for to convert the NOx. So high temperature exhaust valves is required. Exhaust flap valve is required for this. Then water vapor management. There is a chance to mix in atmospheric air to control this. The corrosion resistance material also to be considered. In another big challenge is storage system. We need high pressure tanks uh, around say 700 bars. We need to make a brainstorm on this cylinder design and storage where the cylinder will be stored. The composite tanks, lot of R&Ds are going on this. Few OEMs are working on this. Um, I would say Ashok Leyland, Reliance, and recently um, JCB got certificate, preliminary certificate to use this H2 ICE engine. JCB, then Caterpillar, lot of many OEMs are working on this. Lot of R&D works are going on. Then another safety walls insulation is required. Then crash resistance mounting frames is required. The high pressure delivery system is pressure regulators, two stage, three stage. At the moment, we are using two stage regulators in CNG vehicle, but in this case, three to four stages also may required based on the layout. high pressure line has to be taken care, and solenoid safety valves, durability, lot of component durability is going on with many certification agencies are working on this to arrive safety standard on H2 valves, safety valves. Then another challenge is leakage. Green hydrogen is small molecular size. Since it is a small molecular size and high flammability, there is a chance to mix. High pressure delivery system must absolutely leak tight. So we need to focus on tight connections. ECU interface is the another challenging subject. The custom hydrogen fuel mapping, unlike gasoline or diesel, this is not like that. Hydrogen has wide flammability range and burns very quickly. The ECU requires unique fuel maps to precise control the air fuel mixture, ignition timing, and injection strategies for optimal combustion efficiency, power output, and minimal NOx emission across all operating conditions. So, fuel mapping is the major topic. We need to focus on this. Then, NOx deduction algorithm has to arrive. So, real-time injector pulse control, precise control over hydrogen injection, whether port injection or direct injection is a vital role on this. The ECU dynamically adjust injector pulse with timing based on engine load, speed, and other parameters to deliver the exact amount of hydrogen need for efficient and clean combustion. Safety shut-off sensor integration are also integrated with ECU programming. The safety systems, hydrogen engines, hydrogen leak sensor is required. Then automatic shut-off valves, ventilation duct is very much required for this kind of a vehicle, and a flame arresters is must. Then pressure relief valves is the most critical part of this application. System interface, when we talk about a system interface overview, the hydrogen sensor, fuel concentration data, then hydrogen storage, source of a fuel, then a pressure regulator, injector rail, ECU, temperature sensors. So types of when we talk about types of hydrogen engine technologies, port injection is the one technology, and a dual fuel hydrogen with diesel. Some R&D is going on this. Then a direct injection is the another technology. Hydrogen enriched combustion system. This is the advanced version. The hydrogen enriched combustion system involves adding a small percentage of hydrogen to primary fossil fuel, gasoline or natural gas. Even small amounts of hydrogen can significantly improve the combustion efficiency, reduce the NOx and CO. So a lot of R&Ds are going on these technologies. The performance, when we discuss about performance characteristics of hydrogen engine, high efficiency under lean operation, high torque achievable with direct injection system, but challenges are there in direct injection system, like knocking, ignition. A lot of challenges are there in DI system. Then zero zero CO2 emission tailpipe is the character reduced PM and HC emission. The application of hydrogen engine, heavy duty trucks. Mainly, our government is focusing. The strategy is very clear in 2030. Um, all passenger and light commercial vehicle with hybrid and gasoline and EV. That is the approach. And medium commercial vehicle M&HCV and HCV with hydrogen and fuel cell. That is the a direction and suggestion given by the Ministry of Highway. And another segment is that non-automotive, like tractor and genset, other construction equipment vehicles. They are looking some alternate fuels like biodiesel, blend, then ethanol, methanol, and one more fuel is there, isobutanol, and some of the European Union are working with hydro-treated vegetable oil. Yeah. So lot of this is the approach. Here, no, the heavy duty trucks, they are focusing with hydrogen and hydrogen fuel cell only. The passenger car is very limited, and the generator and stationary power system also, the forklifts and the industrial transport. So we list down all the applications. Our government suggestion and focus is slightly differ from this one. We can applicate this hydrogen engine in various applications. Future scope of hydrogen. This is a bridge to fuel cells. H2 ICE can serve as a crucial transitional technology, bridging the gap between conventional fossil fuel engines and more advanced fuel cell electric vehicles. They allow for the incremental development of hydrogen infrastructure and supply chains while utilizing the familiar engine technology. The cryogenic hydrogen storage research, then DI hydrogen system advancement, global push to net zero mobility. Hydrogen engine offer clean mobility using existing ICE platforms. There is a lot of R&Ds are going to convert the existing gasoline engine to H2 ICE. Some of OEM already did this. I think Ashok Leyland already did this experiment. The existing SI engine converted as a H2 ICE, and some durability run is going on, and the required modification in combustion injection engine architecture. Engine system integration demands a strong safety and control system, promising technology for future decarbonized transportation. So, and when we talk about hydrogen, we know that lot of debates and war and a lot of things is going on around fossil fuels currently. Petroleum, like a petroleum product, lot of politics and a lot of things are going. Our Indian government idea is to minimize or make it zero after 2030. The fossil fuel usage will be the very limited. So we know that a lot of things is going on around the globally, lot of things is going on. We know that, from your side, the faculty has to make the future. That is my point. I want to mention here. You need to develop all the future students towards the H2Is and other alternate fuels like biodiesel, ethanol, methanol. Lot of R&Ds are going on. Many OEMs investing lot on this alternate fuels. Government giving a lot of subsidies for this one. Thank you. Thank you for this wonderful session. Thank you.
Participants, if you have any queries, please post in the chat box or you may unmute your and ask.
Sir, I have one question. I am Lakshmi Narasimhan, the Vice President of GRD Group of Institutions.
Yes, sir.
Yeah, thanks for the nice presentation. And as regards hydrogen safety, could you please throw some points?
Mhm. Are you asking me to present again?
No. As regards hydrogen safety, because I still remember working for liquid hydrogen storage tanks for rockets when I was doing my PhD under cryogenics. Okay.
Yeah.
So there we know some kind of bottlenecks that we had or we faced as regards the hydrogen storage and all. But now, when it comes for vehicles, okay, when it comes for power generation, lots of storage related aspects are to be taken care of. And what is this? Your as an expert, your opinion on that? Even if it is taken for engines, even for example. So where we are placed?
Yeah. The very few, few OEMs already, running vehicle in track. I experienced in Ashok Leyland. They placed over the roof and they are running. That is not the place. Many R&D is going on this, tank design and
Yeah.
location of the cylinders. Mm, as as I experienced, they placed it over the top of the vehicle.
Great. So yet to it is to be understood that we are yet to mature or
Yeah,
already
yet to mature.
mature.
Yes, you are absolutely right. When the vehicle comes to a road, that is different. The running in inside the lab or
Laboratories. Yeah.
test track, that is a different case. So
True.
at the moment, many OEMs under engine development stage only. Very few vehicles running with hydrogen cylinders. Vehicle. Very few vehicles running in test track.
True. Absolutely right. Absolutely right.
Yeah.
Thank you very much, sir. Thank you very much, sir. It was a
Thank you,
very
sir.
knowledgeable, wonderful session from your side. Thank you, sir.
Thank you, sir.
Sir, good evening, sir. One question from Dr. Burla Ramakrishna in chat box.
Yes, sir.
Can we use hydrogen gas to CRDI engine?
Mm, No, sir. Actually, CRDI, as we said, fuel management is different. If we consider no port injection and direct injection, if we consider port injection, the engine architecture will be the different. We cannot use a CRDI. We cannot use hydrogen in CRDI engine. Currently, many players working in port injection, not a direct, a direct injection. That is the one point. And common rail we are widely using in diesel engines. So compression ignition parameters is different, and here we are talking about SI.
Okay, thank you, sir.
Yeah, thank you.
Thank you for all the participants. And now I request organizer Dr. Dileepan to give you a vote of thanks.
Once again, very good evening, one and all here. On behalf of all us, I would like to extend sincere thanks to our esteemed speaker, Mr. G. Dhanasekaran sir, for his incredibly informative presentation today. Sir, you have expertly guided us through entire story of hydrogen, from the promising of green hydrogen production methods, India's strategic 2030 targets, and practical hydrogen engine modifications and emissions that will turn the mission into the reality. Your insights drawn from deep expertise have given us valuable perspective on this critical technology for a clean future. Let us all express our thanks once again to Mr. G. Dhanasekaran sir with a generous ground of applause. Thank you, sir. Have a wonderful day ahead.
Thank you very much. In short time of I prepared this presentation 2 days back only.
Yeah.
Sorry for guys.
No, sir.
This
No,
time
sir.
it's my. I hope I wish to give some more detail, deep detail in green hydrogen production methodology, but I prepared in short time. So next time, if you permit, next time I'll give some more detail. Yeah.
Thank you, sir. Really,
Thank
your
you very much.
presentation was excellent. Now, thank you for making a complex topics and easy to understand, sir. Thank you, sir.
Thank you very much. Thank you all.
Judges, it is my distinct pleasure to welcome our esteemed speaker for today's session 2, Dr. S. Tyagarajan sir. Today, we are truly privileged to have expert who will deepen our understanding a critical area of green hydrogen production, electrolyzer technologies. Our topic of this session is Alkaline PEM SOEC system. It is my great pleasure to introduce our speaker for this session, Dr. S. Tyagarajan sir, Associate Professor at Alliance University, Bangalore, where he brings wealth of knowledge and research experience in the field of energy system and sustainable technologies. His expertise and insights sure to shed valuable sight of nonsense advancements and comparative analysis of these key electrolyzer technologies. Dr. Tyagarajan sir is an accomplished researcher and accommodation currently serving as an Associate Professor at Alliance University, Bangalore, with more than 11 years of dedicated experience. He has established himself a leading voice in the critical field of internal combustion engines and sustainable energy technologies. His academic credentials are truly impressive, holding PhD in mechanical engineering from SRM University and MS in automotive engineering from the prestigious University of Bath, UK. The strong foundation has propelled his pioneering research, which focuses extensively on harnessing the power of hydrogen as a green gaseous fuel for compression ignition engine, dual fuel operation, and innovative method to minimize harmful NOx and CO2 emissions. His contribution to scientific community are substantial. Dr. Tyagarajan has authored over 50 essays SCI indexed research papers, contributed to book chapters, and even hold patents in the vital area of waste to fuel technologies. His groundbreaking work on hydrogen enrichment, carbon capture system, and low carbon biofuel blends has been widely recognized and published in leading international journals. Beyond his research, he is dedicated educator and mentor, inspiring a new generation of students, scholars, and industry professionals through his deep commitment to renewable energy advancement. On behalf of organizing committee, all our participants and GRT Institute of Engineering Technology, I extend very warm and respectful welcome to you, sir. We are all eager to learn from you. The floor on yours, sir. Take over the session, sir.
Thank you so much, sir.
Thank you, sir.
So, today, the topic that we are going to cover is the electrolyzer technologies, alkaline PEM and SOEC systems. So, before we get into in-depth about this, we'll just start with why we need the decarbonization. That is, hydrogen is a carbon-free fuel, but why we need it is basically because of the CO2 emission and also the recent Paris Agreement that all the developed countries and developing countries are moving towards. Okay, so the fossil fuels obviously have CO2 being emitted, and then hydrogen is probably one of the main fuel that can curb this CO2 emission. Of course, we can claim that electric vehicles can do it, but still the electricity that we are producing are mostly from non-renewable resources. Only about 10% of electricity in India is produced through renewable sources. So even if we use electric vehicles, still the CO2 is going to be, if you compare the well-to-wheel analysis, the CO2 is obviously going to be on the higher side. So obviously, hydrogen is future fuel, and we've been a lot of research has been done for past 40, 50 years. And it's not only an energy source, it's also an energy carrier, and it can be produced from various sources, renewables, nuclear, okay, and even fossil fuels, and it can be stored and transported in various forms also. And it can be used in fuel cells, that is a hydrogen fuel cell, which is getting popular in recent times. It's called as a clean fuel because it does not have any carbon to it. So combustion of hydrogen is obviously going to give you only the water vapor. So with respect to the production, we mostly produce hydrogen only from the natural gas. Okay, that is the steam methane reforming. But one of the major problem is the high CO2 emission, about 95%. Then after some research, we came to something called as blue hydrogen, where the CCUS is being used. That is carbon capture. Either carbon is captured through either absorption or adsorption, or it is converted to some other form. Okay, so like this, the hydrogen was produced using that. It's the same technology as the gray hydrogen, but only one thing is the CO2 is reduced to some extent. But of course, we cannot eliminate the CO2 completely. We can reduce from 95% to about to 50%. Okay, that's the maximum that we can do. Green hydrogen is getting popular nowadays. That is because it is produced through the water electrolysis, and most importantly, if we use the electricity from the renewable sources, obviously it is the one of the sustainable pathway. So what are the benefits of hydrogen? Why we are talking about it? Why you need to produce the hydrogen is, first thing, as I already told, combustion produces only the water vapor because it does not have any carbon. Energy density, or we can say the calorific value, is about 3 times as that of gasoline or diesel. It's about 120 megajoule per kg. And it is very versatile. It can be used in fuel cells, it can be used in turbines, engines, and a lot of applications we can use hydrogen. And another very important thing is it can be stored for a very, very long time. Unlike any of the, even the diesel will have some problems or long storage, but hydrogen will not have that problem. So decarbonizing, one of the major feedstock, hydrogen can be used. Now, we have talked about the advantages. Now, what is the problem with this is, one thing is going to be the storage and the transportation. Okay, so because it's very, very difficult, and also it is costly to store because of the low volumetric density. Production cost, of course, the green hydrogen is obviously in the sustainable way, but the production cost is very, 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 very high and compared to the gray hydrogen. That's why most of the hydrogen are produced only, we are producing only the gray hydrogen. We are not going to green hydrogen because currently the production cost is very, very high. And most important, why we still don't have hydrogen, direct hydrogen fuel cars on road is because of the safety. It's very, very highly flammable. It has a wide flammability range and a low ignition energy, and its flame is invisible. Okay, so these are with respect to the safety aspects, and we also lack the infrastructure in the production, distribution, and the dispensing. And one of the important thing is the hydrogen embrittlement on some metals. So this is what I've been telling you. The flammability limit, the ignition energy is very, very low. So even a small spark can ignite it. Flame speed is very, very fast. And one of the important problem is the flame flashback, which means that once it's getting combusted in the IC engine, it can come back to the cylinder and it can burst. So how we can store the hydrogen is, one thing is in terms of the compressed gas, which is very, very common. So we are compressing it in the pressure of 350 to 700 bar. It's a fast filling and also fast discharging as it is in gaseous state. But one problem is the high energy cost for the compression. Liquid hydrogen mostly used in aircrafts and space shuttles as of now. It is cryogenically, it's been stored at minus 253 degrees C. It has a very good volumetric density compared to compressed gas, but the problem is the high cost of liquefaction and also the boil-off losses. So when it is changing the state from liquid to gas, there are some losses that we see. And in recent times, there are a lot of research has been done in the metal hydrates. Of course, metal hydrates are good, but again, it also has a problem of the cost. How much cost effective it is going to be another problem. But one thing is metal hydrates is very, very safe compared to the gaseous and also the liquid. So in recent, what they are doing is they are using an adsorbents where the hydrogen is stored in the adsorbent and then it is released whenever it is necessary. Okay, so like something like an activated carbon or something like that. So it has a very good kinetics and it is fully reversible. But again, the problem is going to be the cost and also the wastage in this things. Okay, so coming to the production, how we can produce the green hydrogen. So this is a very basic thing. We all know the water with electricity is going to produce hydrogen and oxygen. It's a very simple thing, simple physics. Now, what is the problem with this? This is so simple. Okay, so we have an anode and cathode in the water, and water is going to be converted to hydrogen. What is the problem with that is going to be only the mass. So the amount of hydrogen that we require cannot be matched with that. Okay, so we need a large infrastructure for this electrolysis. Okay, so that is why we are doing a lot of modifications in increasing the efficiency, how much amount of hydrogen can be produced, and also minimizing the energy that we are consuming. So basically, it has the cell, it has an anode and cathode, and there'll be stacks. Okay, it will be connected in series, and you also require DC power and the water purification, RO water, because contaminated water again it's going to contaminate the hydrogen that is produced. So these are all some of the important things that are required. In electrolysis, one of the important thing is the unconverted energy generally creates heat, and again that is also going to be an issue. So we need an active cooling system to prevent the systems overheating. So the topics that you are going to see, obviously the alkaline electrolysis (AEL) and then the PEM, and then recent research is the combination of these two, which is AEM, and also of course the solid oxide, which is the latest trending research. So, the minimum energy that is required to split the water, okay, how much energy is required can be given through the Gibbs free energy of the reaction. So that has been given here, and also the enthalpy required is also total energy, that is combining the PV and the internal energy, we get the total enthalpy here. And minimum cell voltage can be found out by the Faraday's constant and the cell potential. Why we need real cells more than voltages? Because of the losses, okay, and also the theoretical. So along with the theoretical voltage, what we are calculating, there's 1.23 volts. there will be some losses up to 1 volt. So the operating actual voltage will be approximately near to the 2 volts. So what are all the performance losses that we can see when we are producing hydrogen? One thing is the catalyst dissolution. So the active material into the catalyst, the loss of this active material is going to be the one of the major issue. Another thing is the membrane thinning. So when this chemical reaction keeps on happening, after some time, what happens? The membrane gets reduced actually, and also the corrosion. That is one of the major problem, and of course the leakage. So coming to the alkaline electrolysis, now it is one of the very mature technology, and it's commercially being used in all the industries also. And of course, we can also do much more research in this, but still there are some these things. Okay, so um, so basic principle is obviously we'll be having a high concentrated alkaline solution, typically used as KOH. NaOH can also be used. That is for the conducting ions between the electrodes. So in the cathode, if you can see that, you will be having what's going to happen is water is reduced to the negative electrode in the cathode. The hydroxide ions are produced and it goes to the anode. So and then again it is oxidized in the positive side, and then the oxygen gas is liberated in that point. You are having a separation barrier. So that is between these two things. Okay, that barrier that is a diaphragm that is kept between these two to prevent both the hydrogen and oxygen being mixed, so that we get the pure hydrogen out of it. So now the latest thing, as I told, of course, this is a very traditional one where we always had a gap between the electrodes and the diaphragm. Okay, so approximately 1 to 3 gap was always there. But now the zero gap architecture is where there is no gap between both the electrodes and the diaphragm. Okay, so electrodes are actually pressed directly to the diaphragm in this case. And obviously, ohmic resistance, that the resistance to the flow of current is actually high for this, but it is actually minimal in this in the zero gap architecture. The current density is also very low for the traditional type, and where the gap is there, here it is actually good because of the stack is very compact. Okay, it is very nearby. That is the reason the current density is actually high. Of course, complexity, the gap is going to be very simple to make, but here you require a lot of things, a lot of meshes, a lot of springs to actually keep it together. So that is one of the complexity in with respect to the construction of it. Right. So what are all these separators that we have been using? The ceramic and polymer composites is very common thing. But nowadays, what people have gone to the composite materials like zirconium oxide and zircon. So all these things, they are having very high durability and also the good conductivity. And most importantly, what happens is that decay of these materials is actually less due to the chemical reaction. So which is one of the disadvantages that we saw, or the problem that we saw previously. So because of that, these types of polymers, the composites are being used very commonly nowadays. So with respect to the operating condition, we can see that it's operating typically less than 100 degrees Celsius within the range of 60 to 90. Approximately 75 degrees is the optimum that all the retorts or is being operated actually. If we go for a very high temperature, why can't we go for temperature higher than 100 degrees Celsius? Obviously, the kinetics is going to improve. The ions are going to move very faster. But what happens is the diaphragm degradation will be very fast, and also the gas purity will be very less. So that is the optimum temperature that has been followed. Again, the current density is also maintained between 0.2 and 0.5 ampere per centimeter square. Okay, and also the operating pressure is kept within the 30 bar, because more pressure means there will be a problem with respect to the sealing. And again, what are all we are doing is only for two things: one, to get a very good efficiency from the system; another one is to get a pure hydrogen. So along with the electrolyzer, okay, what are the other things that is required for the hydrogen to be produced? So we need, as I told you, we need an RO water unit that is kept here. Of course, we need a DC, so AC to DC converters required to be sent to the electrolyzer, and we also have a lay tank and pump for that. And we also have a hydrogen gas separator where it separates the hydrogen, where you get the pure hydrogen. And we also have an oxygen separator there. Separate cooling system has also been provided for this. So because when hydrogen is produced, always remember, from the electrolyzer, we will never get a pure hydrogen. Okay, so we have to do some filtering process. That's where the hydrogen gas separator is kept, and then we get the pure hydrogen. And also the dryer is there because there will be some water molecules that will be present along with the hydrogen. So these two stages are very, very important to get the pure hydrogen. So the water purity is one of the most important things. So these are all some of the things that requires to get to the very pure hydrogen that we require. So we cannot achieve obviously 100%. So at least to 99.9% we can achieve. So one of the most important thing is we generally use the RO water for this. Okay, reverse osmosis, which has very good this thing purity, water purity. And also the hydrogen cleanup, as I told you, it's very, very important after the hydrogen is produced from the electrolyzer, because it will have some water molecules. It will also have some trace oxygen in it. Okay. So for reaching the highest purity, we need to use this hydrogen purifier and also the dryers. Okay. So these are some of the things that are required to get to the purest form of the right. So what are the advantages? It's obviously a very, very old technology and a proven technology. It's already been used in most of the industries. And initial capex, that is the initial money that is put, is very, very low, and it also has a very good lifetime. It can also be easily scalable for the industries. Okay, so that is one of the major thing. What are the problems is the electrolyte, because the handling the KOH is actually a bit of the problem, and the electrolyte keeps to corrode very, very easily. That is one problem. So that comes under the running cost, and also the low current density. That is one of the another issue with that. Cold start, there are a lot of problems during cold start. Of course, with the next things, PEMs and other SOFCs, we have reduced that. We have got to that problem is being solved in that. But here we have a cold start problem, and also it all obviously operates under very, very low pressure. Hence, you require a compressor to get the hydrogen stored into some this thing. Okay. So these are some of the things. And at very low loads, what happens is the efficiency actually drops because of the impurity risk. So degradation in alkaline system, as I told, one important thing is going to be the catalyst poisoning. Okay, so after some time, what happens is these gets deposited on the cathode, and it actually blocks the active sites. And also another very important thing is the diaphragm blockage. So what basically happens is the pores gets clogged, and it creates more and more resistance, and it is just very difficult for the hydrogen to move from one end to the another. Yeah. Okay. And also the anode passivation. Again, that is also another major issue. So now, what are some of the latest technologies or latest research that has been done? Of course, we'll discuss more about it. But as of now, what are all the things that has been done? Is one thing is the aqua technology. They are using some novel electrode materials to improve the gas bubble release dynamics. Same thing, the bubble management they have done, and also the balance of the plant has been reduced, where we can the design the design that I showed was a generalized one, but they have done some research to reduce the balance of the plant and also the direct gas extraction through it. And of course, the diaphragm integration zero cap architecture has been implemented for the maximum efficiency and also to improve the gas purity. Okay. So next, coming to the PEM, which is the proton exchange membrane technology. So again, here in all the things, we are going to do the same thing. We are going to split the water into hydrogen and oxygen. How effective we are going to do is more important in this case. So what here we are having is a proton exchange membrane, which separates the electrodes, and it conducts the protons between this, and also the water is split at the anode to form the oxygen, and the hydrogen ions. And what happens is hydrogen will migrate through the membrane to the cathode. The typical operating temperature is almost similar to that only. It is about 250 to 80 degrees Celsius. And one of the important thing is going to be the membrane must be always been hydrated for conducting, for the protons to conduct. Okay, so that is one thing. That is the reason we have to keep it the temperature below the 100 degree Celsius. So this is how it basically looks. As you can see here, at the anode itself, the oxygen and hydrogen is being split, and then the hydrogen actually moves to the cathode side. Okay, so there is a membrane that has been in between it. Okay, and as you can see, there is no any gaps or something like that in this, like how we saw in the previous one. So here there is no any gap, and generally is the anode and this thing are very effective in this case, because we are achieving very good efficiency in this PA. So, what are the membranes that we generally use is going to be then polymers like Nafion. And as I already told you, it has to be it needs to be hydrated always, and its the working temperature is actually lesser than 100 degrees Celsius, typically maintained under 80 degrees Celsius mostly. And the catalyst that is used is the premium platinum, this thing, because of the acidic environment it is required. So, platinum for the cathode and iridium oxide or the ruthenium oxide for the anode. This is a general catalyst that has been used. And between this, there is a bipolar plates or that has been kept, that has been coated with titanium. And nowadays, titanium alloys are being used. That is that is actually good for the corrosion. Okay, rather than using a stainless steel like in alkaline systems. But of course, the cost is going to be higher, but still the life time is going to be okay. So what are all the advantages that we get is, one thing is obviously the hydrogen purity will be better. Another thing is the response time is going to be better compared to the previous one, and the current density is going to be higher as well. It is more compared to. Okay, so PEM have these kind of advantages, and of course, if we are pairing it with renewable, will be getting the very good green hydrogen out of it. So, the with respect to the cost, it is obviously it's very high because the platinum and the iridium cost is very high, and the corrosive, the titanium alloy is also significantly high, and also. In 3 to 5 years you have to change the catalyst. Okay, and also the because it will degrade after that. So again, these are all some of the running cost, on the initial cost is actually high for PEM. So that is why it is not widely being used in industries because of the initial cost. So to give you a brief comparison about the alkaline and the PEM. So here it is a liquid base, that is KOH solution, it is corrosive, but here we are using only the solid, which is an polymer membrane, that is a Nafion material that is generally being used. Operating temperature is somewhat similar to both. Pressure is actually less than 3 megapascal in the AEL, but in PM, it is the this thing is up to 3 to 8 MPa it can go. Again, the current density is very low or moderate with respect to AEL, and with PM it is actually higher. The response time is very fast for PM compared to the alkaline, and because of that, it has a very good efficiency as well, and the purity is actually highest for the PM compared to that of the alkaline. And one of the major problem is going to be the capex. Okay, so because of that, non-noble metals being used and stainless steel is being used, all these things, the cost of AEL is less compared to that of PEM. And as I already told you, because of that, most of the industries prefer alkaline electrolyzer rather than the PEM electrolyzer. Lifetime, it's about approximately about 10 years for the alkaline one. PEM, it is about 3 to 7 years. As I told you, after that, the catalyst needs to be changed. Okay, so that is one limitation with respect to the PEM. So here, there is not much change with respect to the balance of the plant. Here, you say the same DC supply. You have the PM stack here. Because here also we need the water, because as I told you, it needs to be hydrated always, and water is there. We have a separate hydrogen and water separator, because when the hydrogen is produced, obviously there will be more water in this case compared to the previous one. So also we have a hydrogen dryer. So the water separator, because the previous one we had hydrogen oxygen separator, but here we are having hydrogen water separator, oxygen water separator. Okay, and we are also having a the heat exchange has been connected with these two, so that the separation process is quick. So the pros and cons, of course, the design is very, very compact, and it has a very good dynamic response, very good purity, good pressure capability, and also it's very, very safe, because we are using a solid electrolyte unless liquid, and hence the gas mixing can never happen. So that is one of the major advantage of this. Of course, the limitation, as I told you, cost and the lifetime is the one of the major limitation. And another very important thing is we need the deionized water required for this. Okay, so to prevent the membrane degradation. Okay, so that is one another one thing. The water quality has to be in the purest form. Okay. Now, combining the benefits of both alkaline and PEM, we have something called as AEM electrolyzers, which is not in this thing that famous, but still the researchers have been successful, and it is actually better than it's combining the advantages of both alkaline and PEM. So as such, as you can see that it has an hybrid advantage, okay, where it again uses a solid polymer, where it is having an the transfer is happening between the membrane from the cathode to the anode. Now, what is the advantage in this is, in alkaline we have a non-noble catalyst, okay, and that is being used along with the PEM, where you can be having a compact design as well. Okay, so compared to the alkaline solution type, this is better because in material cost, compact design, and the safer electrolyte, these are some of the major advantages with respect to this. Some technical challenges are still there. Okay, so these needs to be addressed. Obviously, the membrane stability is one of the major problem, and the conductivity, and also the manufacturing or fabrication is bit complex in this case. So a lot of research has been going on in this area, in this AEM, combining these two. So the next one is a solid oxide, which is we call it as SOEF, and this is one of the what to say, proven thing, and a lot of research has been done in this, uh, and this is one of the what to say, advantages compared to all the other things. So here, what we are basically using is a solid ceramic electrolyte in this case. Generally, yttria based zirconia has generally been used. So, what it does is it actually conducts the oxygen ions at a very, very high temperature, and that is why we don't require any liquid electrolytes in this case. And here, instead of supplying the water, we are supplying the steam at the cathode. Okay, so that is one of the major advantage in this case, because what happens is your lifetime actually increases, one thing. Another thing is you don't need a dryer or any other thing to for getting the water, separating the water. Okay, that is one thing, one major advantage in this case. So the electrical efficiency is actually about 90 to 100 percentage. Okay, because the heat, the waste heat is also can also be used back, so that the good efficiency can be achieved with it. Okay, so the heat can be used to convert the water to the steam. Okay, so the way heat can need not be wasted. Okay, that can be direct again used to steam the water. So in that case, we can achieve very good this thing. And obviously, it is operating at very, very high nature. So here what we are having is we are having a water, we are having a steam generator, and we are also having a mixture, and that feed gas is going to the SOEC stack. Okay, so now here what we are actually getting is we'll be getting something called as syngas. Okay, so syngas is nothing but the mixture of H2 and CO. Okay, that is the syngas. Okay, so from that we also from the if we do the fuel synthesis, we can even get methanol. Okay, or we call it as the Fischer-Tropsch fuels also we can get, and it can also be because nowadays we are also adding the ethanol and methanol to it, and methanol is obviously going to come soon in our country as an alternate fuel mixed with gasoline. Already we have ethanol, and now the methanol will also come soon. So this is one of the major advantage with respect to this. Here, of course, we are not getting the pure hydrogen, but still this is an hydrogen carrier. So instead of hydrogen, we can use this. Okay, so it has the same advantages, but one thing is the what to say the problems with respect to hydrogen gases can be eliminated when we are using these. So of course, when we are using the solid oxide electrolyzers, we can get very good efficiency when we use the waste heat, obviously, for converting the water to steam. And it operates at a very, very high temperature of about 800 degree Celsius. And also the specific energy is also, it's going to be very, very high in this case. Now, what are some of the problems? Is obviously one thing is the thermal degradation, mechanical failure. That is one thing, and system complexity because of the lot of steam generation, heat recovery. It becomes like a closed loop system, and the system gets actually complex in these cases. And also, sealing is one of the major problem with this type of SOECs. Okay. Now, with this we saw various types of therapers. Now what we are going to discuss is what are all some of the new things, technologies that has been actually been done in this one. Okay, just one second. Yeah. So this is just an summary of what we have seen till now. So alkaline is obviously used in large scale industries. PM is generally used in the variable transport things like that. And AEM is now it is a very low cost potential, and now it will be in market soon. And SOEC is actually it is industrial heat integration they are doing, and also for the syngas fuels, also they are doing this. That obviously the response is going to be very very slow with alkaline and very good with PEM, and it's good with AEM as it is combining both, which is somewhat similar to that of PEM. But with respect to SOEC, if you see the dynamic response is actually we see it as a it will be in the steady state. The cost is obviously very, very cheap with respect to the alkaline one. With the PEM, obviously, it is expensive materials are used. It's very, very high. AEM, as it's combined, it is a bit less compared to that of PEM. And obviously, SOEC is the highest because using ceramics with high temperature, those kind of materials are required. We need a separate thing to convert the water to steam. So all these things are there. With respect to complexity, we can see that the alkaline and the solid oxide is very very complex in terms of the this thing, and the PEM and AEM are actually a bit less. AEM is actually very very smaller one, and it is also very very compact. With respect to the purity, if you see, obviously the highest is going to be the SOEC and the AEM, and PEM is also obviously good. Alkaline is it's only for the mass and where we don't much worry about the hydrogen purity. But when we have to go to the hydrogen purity, we have to go to the PEM or AEM or SOEC. So, in the last 5 years, what are all some of the recent research that has been done in these technologies? Is just I'm just going to discuss what are these done. So, because this can be useful for you to, if you are doing research in this, you can take it to the next level, or you can see what can be done, how this problem can be solved. Right. So this is one of the research that has been done by Zhang, obviously. What they have basically done is obviously a zero gap cell architecture with KOH 30% of weight at a very, very low pressure. They have built it. The materials that they have used is what they have changed. Okay. So nickel foam and also the reinforced diaphragm, PTFE reinforced diaphragm that they have used, and they have achieved a very, very good performance by using this. Okay, so this is just the author and citation. So if you require, you can note it, and probably you can read the full paper if you are interested in that. So in another paper, Liu et al., what they have done is they have used an LDH technique, which is an layered double hydroxide. Okay, nano sheets they have used. Okay, again the KOH percentage was the same, and also they have actually retained 95% of the activity after 1,000 hours, which is actually really, really good. And they also say that this is having a very good lifetime this thing. Okay, so that is one of the major advantage of this. With respect to the electrolyte design, Wang et al. Has done a change in this. So he's made an nickel and this thing foam, and electrospun NIFE nano fiber mats used to reduce the bubble coverage, obviously, and also the ohmic drop has also been very, very good. So they have observed that their overall cell efficiency and the durability was very, very good because they have reduced the resistance, and also the mass transfer was better. Jenner et al., what he has done is he has done an innovation in the diaphragm where the zircon ADV and the polyether sulfone separators were being used, and also they also found that the hydrogen crossover was very, very minimized. So that is the reason they could achieve a very good pure hydrogen out of it. Right. So here to improve the stack efficiency, okay. So what they did was they incorporated an institute of water purification to maintain the high efficiency and the durability. And as the water was very, very pure, they were able to achieve very good stack efficiency in this case. And there was also a research with respect to the coating and the corrosion. So what they have made is the 5 nanometer of TIN has been coated on the stainless steel, and also they have seen that how much the degradation for over 8,000 hours. So these are some of the things that has been done, how the capex can be reduced, and how the large scale deployment can be more economically viable. So these are some of the research that has been done. Okay. So this is with respect to the alkaline one. Okay, so next we get into the proton exchange, where here the Kim et al. Has what he has done recently is he has used the core shell, and he is able to achieve 1.5 ampere per centimeter square at the very, very low voltage. Okay, and they have reduced the loading and also maintaining the very high performance and durability. So that was one of the things that is achieved by using this. And also the catalyst layers. Okay, Frindich et al., what he has done is the catalyst layer thickness he has reduced, and because of that the nanometer he has used only 200 nanometer. Okay, and so because of that, what happened was actually the response time was also increased, and also the hydrogen purity without affecting the hydrogen purity and the performance. So this is one of the area that the catalyst we can work on. And with respect to the membrane advancement, obviously the membrane, the graphene reinforced Teflon is one of the research. A lot of research has been done in that. So that is basically they have checked the performance under the dynamic operating conditions by varying various conditions, and they also said that it enhanced the membrane stability, and also the performance was also in par with the normal one. So this paper specifically for the better gas removal. Okay, so this is one of the good research paper actually, because what they have done is for removing the gas properly and from the electrolyzer. Okay, so what they have done is they have designed an own channel, and so that it can be transported without affecting any of the this thing. Okay, so that is one of the optimization that they have done. So Again, in the Siemens Energy report, what they also demonstrated is how the electrolyzer can be working stable with a lesser this thing for less than 4 ampere per centimeter square. So high current density they were able to achieve, and they also say that because PMs is mostly it is not suitable for large scale, and mostly all of the research focuses towards using it to the large scale. Okay, because large scale obviously the capex is very high, and most of the work are towards reducing the capex. That is one part of the research that has been done. Okay. So this is another good this thing where they have a lot of PM stack, and this one was for large scale deployment for higher hydrogen production. They have made a good design with this one. So basically, the all of the research actually goes towards the reduction of the capex, okay, the cost, initial cost of this and of the PEM, because the industry deployment, because it has very good advantages. Only thing is the cost, which is going to be, which is generally about 5 to 6 times than that of an alkaline one. So that is the reason the industries are still yet to get to it. So, with respect to the solid this thing, there are some of the research also been done in this. Okay, so they used the cell. They designed by using the ferritic stainless steel, which can go for a very longer run and also at a very high temperature. Okay, and that is one of the things they said that the thermal shock resistance was really good, and obviously the performance can be improved when